Okay, last Tuesday we studied how to analyze a heat exchanger when we have two different fluids are exchanging heats. In this case, we have fluid A and fluid B. So by analyzing their energy balance, we can find three energy balance equations: one for fluid A, another one is for fluid B, and the last one is when we consider the entire heat exchanger is our system. So we can use the first two equations if we are interested in this rate of heat transfer Q dot. If not, we can use the last equation here. So based on this, let's solve this problem together. We have a steam power plant. This steam power plant has many components in the plant, and one of them is a condenser. Condenser is a device to remove waste heat from the thermodynamic cycle in a steam power plant. By the way, the thermodynamic cycle in the steam power plant is called Rankine cycle, and we are going to study Rankine cycle later in chapter 8. So in this Rankine cycle, we are going to produce high temperature steam. And this high temperature steam is going to expand in a turbine, and the power produced by this turbine is going to run a generator to produce electricity. And after this steam expands, the low pressure, low temperature steam is going to exit the turbine, and we need to remove the waste heat in the steam. So this steam is right after a turbine, and we are going to use water from a nearby river to remove that waste heat. So this is how it works. So we have a steam generator. So that's where we provide heat into water, and then this high temperature, high pressure steam is going to enter this turbine. So this one is steam generator. And this one is a turbine where we produce mechanical power, W out. Then once the expansion of the steam, any leftover steam is going to be removed. And this, the thermal energy of this steam, which is the waste of energy, should be removed, so we can use that steam again, pump this steam back to the steam generator. So we use a condenser. Condenser means a heat exchanger where we pump water so it's a cooling water enters this condenser, so we can remove heat from the steam. And this cooling water is going to, return back to the source. Could be a lake or a river or an ocean. Then steam goes back to the steam generator. However, it has no power, so we use a pump. To pump back this steam back to this steam generator. So here we have the rate of heat transfer Q in. We heat this steam to increase the pressure and temperature. Then it goes to a turbine, expands. And while during the expansion of this steam, we can produce this mechanical power that is going to run a generator. Generator, plus, minus. So that's how we produce electricity. And once the expansion is over, the steam still has waste heat. So we need to remove this waste heat by this cooling water. That's where we remove heat to that out. And then, it goes back to this pump to increase the pressure so that it can go back to this steam generator, W dot in. So this is a typical Rankine cycle. Very famous and the most widely used thermodynamic cycle to produce electricity. And what we study here, this heat exchanger, is this condenser. So this condenser is this one. So you can see this steam enters this condenser. That steam is from this turbine. So you can see the pressure is very low. After the expansion, pressure is only 20 kilopascal. And we want to remove waste heat. And once we remove waste heat, the steam condenses to saturated liquid and goes back to this pump, so it can go back to the steam generator. So it can be a cycle. So we can produce electricity continuously. So that's what happens to produce electricity that we use here. However, we do not want to mix this steam and the cooling water. That's why we use this heat exchanger, so the water does not mix with the steam. And many traditional power plants use water as a coolant. So that's why when you find the power plant, they are built near a lake, usually here near the Michigan Lake or nearby a river, so we can use those water as a coolant by killing those fishes inside, right? That's why, and if you increase the capacity of this power plant, you need to have larger amount of water. That's why, the most giant nuclear power plants are built near a coast, so they can use seawater, which is pretty cheap and abundant, right? So let's study how we can analyze this. Let's see how we can analyze this condenser. So we have information about the inlet of the steam. So we know the pressure and the quality. By the way, we have a quality, which is 95%. If you have a quality, that means the phase change process of the steam is going to be number 3, saturated mixture. And we have the mass flow rate. So we have everything in the inlet of the steam. And if the steam is to leave the condenser as saturated liquid at 20 kilopascal, so we have information at the exit of the steam. So analyzing the inlet and the exit of the steam is not a problem, because we can do that. It's a typical table problem, right? Because we know the temperature and pressure and quality and the phase change processes between the inlet and the exit. Now, what about this cooling water? We know the temperature rise is going to be 10 degrees Celsius, and we want to determine the mass flow rate of this cooling water. That means we need to use the energy balance equation for this heat exchanger to determine the mass flow rate. So let's do that. So first, the simplest schematic of this heat exchanger looks like this. By the way, this is just the simplest one. If you build a heat exchanger in this form, that is not right, because the reason is that there's not much, the surface area where we can exchange heat. So we usually design a heat exchanger trying to increase the interfacial area between two fluids. So usually we add a lot of fins. If you open the engine room of your car, in front of your engine, what do you see? Radiator, right? They are an example of heat exchanger. You see a number of, the fins, so that we can increase the, surface area between the coolant and the air flowing, so we can increase the rate of heat transfer between coolant and air. But similarly, when we design a heat exchanger, we also need to design in the way to increase the surface area. But I use this schematic just to show that, because this is the simplest way to understand, to analyze thermodynamically. So this is the inlet of the cooling water. So I'm going to say number 1, and here is the exit of the cooling water. So number 2, and the inlet of this steam is going to be number 3. The exit of the steam is number 4. So we have mass flow rate m dot number 1, m dot number 2, m dot number 3, and m dot number 4. And what is the relation between mass flow rate? We can apply mass balance equation, conservation of mass for the steam. So the steam has only one inlet, number 3, only one exit, number 4. The mass flow rate of the steam is constant. That means m dot number 3, which is the mass flow rate of the steam at the inlet, should be the same as the mass flow rate at the exit. So I can just say m dot of steam S. So that is the mass balance equation for the steam. What about the cooling water? The cooling water has only one inlet and only one exit, so the mass flow rate of the cooling water is also constant. M dot number 1 is the same as M dot number 2, and that is just the mass flow rate of the cooling water, so I'm going to say M dot of C. So these two are mass balance equations. Then what about energy balance equation? By the way, we want to determine the mass flow rate. We are not interested in the rate of heat transfer between the fluids. So we don't need to, use the first two equations. First two equations here, these two. So let's use the energy balance equation for the entire heat exchanger, which is this one. By the way, if you do not remember the energy balance equation for the entire heat exchanger, don't worry about that. We can find that equation easily. Okay, so this is the control volume, the entire heat exchanger. So how can we find the energy balance equation for this heat exchanger? Always start with the general energy balance equation, Q dot in plus W dot in plus M dot at the inlet. This M dot has what? Specific enthalpy, kinetic energy, and potential energy. It's going to be Q dot out plus W dot out, and mass leaving this control volume, M dot out. This M dot out has three forms of energy: specific enthalpy, H out; specific kinetic energy, velocity square over 2; and potential energy, gravity times elevation Z. So from this is the general energy balance equation. This is the equation that you are going to write on your formula sheet, right? So let's see how we can change this general energy balance equation for this heat exchanger. First of all, there's no information about heat loss, so you can neglect any heat transfer from this control volume to the outside, or from the outside to this control volume. So that means we can neglect Q in and Q out. Does it produce any work, or does it consume any work? No, there is no energy transfer by work. So you can neglect W dot in and W dot out. Any significant kinetic energy change? No, so you can neglect kinetic energy change. Potential energy change, you can neglect that too. Then what do we have? The rate of enthalpy at the inlet and the rate of enthalpy at the exit. So how many inlets do we have? 1, 3. How many exits do we have? 2, 4. So 2 of them, 2 of each. So let's use 1 and 3 first. M dot H is the form. So M dot of what? Number 1. H of what? Number 1 plus number 3. M dot number 3 times H3. And the rate of enthalpy at the exit. How many exits? 2. 2 and 4. So M dot 2 times H2 plus M dot 4 times H4. Now, how many variables in this equation? 1, 2, 3, 4, 5, 6, 7, 8. Are we happy? No, these are too many. So let's use these energy balance, mass balance equations to minimize the number of variables. How can we do that? M dot number 3, M dot number 4, they are just M dot of S. Number 3 and number 4. Number 3, this is just M dot of S. Number 4, M dot of S. What about number 1 and number 2? They are just M dot of C, M dot of coolant, cooling water, M dot of cooling water. Now we have M dot of C, M dot of C here. So we can move this one to the other side. We have M dot of S here, M dot of S here. So we can move this one to the left-hand side. So this one to the left-hand side, this one to the left-hand side, no, right-hand side. Then the energy balance equation is m dot of S, the mass flow rate of the steam, times H3 minus H4 is m dot of C, the mass flow rate of the cooling water, times H2 minus H1. Now, do we know the mass flow rate of the steam? Yes, 20,000. Do we know H3? We do not know. However, we can calculate that because we know pressure and quality. H4, we can do that because we know pressure and it is saturated liquid. So finding these three is no problem, right? What about here? M dot over C, this is what we want to determine. Then the question is, do we know H2 minus H1? Then, do you remember how to determine H2 minus H1? It depends on the system. So what is the system? Cooling water. What is the source of this cooling water? A nearby river, like a Chippewa River. So what is the phase of the river? Steam, ice, just water. So is there a phase change? Not necessarily. So even though this is water, we don't consider it as a phase change material. Can we say this is just pure liquid? No. So if you go to the island park, there is a river. Can you assume that it's a phase change material? No. Can you assume that it's a pure liquid? Yes. So for cooling water, which is far away from the steam, so it is okay to assume it as a pure liquid. Then how do you determine H2 minus H1 if you have a pure system? You can use specific heat. If you don't remember, you know the specific heat equation from chapter 3, so let me write it for you here. H2 minus H1 is CP T2 minus T1. U2 minus U1 is CV T2 minus T1. Now we have a pure water here. Can you find H2 minus H1? Yes, it's going to be CP T2 minus T1. Then what is T2 minus T1? The temperature change of the cooling water. What is the temperature change of the cooling water? 10 degrees Celsius. So this is going to be 10 degrees Celsius times the specific heat. What is the specific heat of water? We can find it from a table. So from this equation, now we only have one unknown, which is the mass flow rate of the cooling water. Can you determine this one? Yes, that's our plan. Okay, let's do that. The first one, m dot of the steam. It's a 20,000 kilogram per hour. 20,000 kilogram per hour. Do you like hour? No, we prefer second. So 1 hour is how many seconds? Yeah, 3,600 seconds. So that's how you determine the mass flow rate of the steam. Now, H3. How do you determine this H3? It depends on the phase change material. By the way, this water and this water, they are not the same. This is a cooling water, so we assume that it's a pure liquid. However, this is steam. Now it is a phase change material, right? So let's find this H3. How can we do that? At the inlet of the steam, we know pressure, and the quality X is 0.95. When you have quality X, that means it's a saturated mixture. If you have a saturated mixture, how do you determine its property? Linear interpolation. So what is the linear interpolation equation? HF plus quality X times Hg minus Hf. Then how can you find Hf and Hg? From that pressure, 20 kilopascal. From this pressure, 20 kilopascal. 0.2 bar is 20 kilopascal, right? So where is Hf? Here. Where is Hg? Here. So this one is Hf 251.4. 251.4. This is Hg 2609.7. What about this quality X that is given? What is the quality X? 95%. 0.95. So that's how you determine H3. Now H4. What is the phase change process? Saturated liquid. So what is the specific enthalpy of saturated liquid? HF. So this one is saturated liquid, so at the HF. At what condition? Saturated liquid at 20 kilopascal. So HF at 20 kilopascal. So that's how you determine H4. So what is HF at 20? Going back to this pressure table, at 20, HF is 251.4. 251.4. Now, how do you determine H2 minus H1? By using this specific heat equation. H2 minus H1, this equation from chapter 3. So H2 minus H1 is going to be, so this whole thing is going to be m dot of cooling water times specific heat times T2 minus T1. By the way, T2 minus T1 is what? 10 degrees Celsius. 10 degrees Celsius. Then what is the specific heat? Cp. Cp can be found from this table A19. Table A19, properties of selected liquid. So for water, specific heat is a function of temperature. And since we do not know the temperature of the river water, we only know the temperature rise. You can assume that the river water is around room temperature, so it's reasonable to select 300 Kelvin. So what is the specific heat? 4.179. So this one is 4.179 kilojoule per kilogram Kelvin or degree Celsius, doesn't matter. Then what is the m dot of C? Now we have everything but m dot of C. So you can determine the mass flow rate of the cooling water. So if you find, you get 297.8 kilogram per second. $300 kilograms per second. That's a lot of water. So for cooling system, in a power plant, we need a lot of water. That's why we built a power plant near free coolant, which is lake or river. Just for your information, that's what we did in the past, the 50 to 100 years. Now, we understand, using this water from nearby river or lake can damage the environment. So we are kind of moving in a transition to air cooling system rather than water cooling system. So if you Google, the newly developed power plants, you can see this giant tower, their water cooling system. instead of their air cooling system instead of water cooling system. Okay. By the way, look at that. 10 degrees Celsius increase in the temperature of river. Imagine that, that we just increased the 10 degrees Celsius. We just increased the temperature of the Chippewa River by 10 degrees Celsius. Do you see any fish there? No, they're gonna die, right? Imagine that the weather in Michigan goes up by 10 degrees Celsius. Not bad, but let's assume that you're in Texas, going up 10 degrees Celsius. Too bad, right? So we are prefer using air cooling systems. So that is one of the transitions, one of the hot topics in power plant industries these days. Any question about this problem? Oh, so here's the solution. No question, right? Because thermodynamics is super easy to understand, isn't it? Okay, so we have one last part. So we use this energy balance equation, which is valid for steady state open system. So we used this energy balance equation for steady state open system for many engineering systems, including nozzle, diffuser, turbine, compressor, valve, mixing chamber, and heat exchanger. So I think that it's enough, right? So what's the next? So that equation is only valid for steady state open system, but that's not the only open system available. What about unsteady open system? Energy analysis of unsteady flow processes. So when we have an unsteady open system, then what is the energy balance equation? What is the mass balance equation? Those are the things that we want to study at last in this chapter, okay? By the way, since we have studied this thermodynamics and the energy balance equations for closed system and open system for a long time, and now, the finding an energy balance equation for unsteady flow process may not be a problem. So let's do it together. So we can start with the very, very basic energy balance equation. What is that? Energy transfer in minus energy transfer out is going to be the change of energy of a system. So this is the energy balance equation that we studied from day one, right? The first page, there was I don't remember the first page. There was a small player. No, we are comparing kinetic energy and potential energy. Anyway, so 3 hamburgers, 2 poops, and 1 hamburger in the bad belly, right? You remember that? Okay. So let's talk about energy transfer in. So if it is unsteady open system, what kind of energy transfer we can expect? We can think about heat transfer Q. Okay, yeah, we can do that. We can think about heat transfer Q, and we can think of energy transfer by work W. That's it? No, it's an open system. So there should be energy transfer by mass. Energy transfer by mass. By the way, do you remember how to determine energy transfer by mass? Yes. Mass times, then this mass has 3 forms of energy: enthalpy, kinetic energy, and potential energy. So these are the energy transfers into a system. Now, it is an unsteady flow process, so now we are not going to use rate form. So there is no Q dot There's no W dot, it's just Q and W. So energy transfer in, we can think of Q in plus W in and mass transfer that goes into a system plus M in. This one has what? Specific enthalpy, H in, specific kinetic energy, velocity in square over 2, and potential energy, specific potential energy, gravity times elevation Z1. So these are energy transfer into an open system, open control volume. What about energy transfer out of a system? We can think of the same thing, Q, W, and mass minus Q, W, and mass, Q out plus W out plus mass at the exit. This mass has what? 3 forms of energy: specific enthalpy, specific kinetic energy, and specific potential energy. So these are energy transfer in and out. Then how do we determine the change of energy? E2 minus E1. Do you remember how to determine the change of energy of a system? If it is, that is from chapter 3, okay, chapter 3. If it is constant volume, U2 minus U1. If it is constant pressure, H2 minus H1. If it is none of these two, U2 minus U1 plus moving boundary work. Do you remember these three? Yes, from chapter 3. So that's how you determine the energy change of a system for 3 different processes: the general process, constant pressure process, constant volume process. So that's how we determine the energy balance equation for unsteady flow process. What about mass balance? Mass transfer in, M in, mass transfer out, M out. It's going to be the change of mass of the system, which is M2 minus M1, the final mass and minus the initial mass. So that is the mass balance equation. So this one is the mass balance equation, and this one is the energy balance equation. That's all. Now you can solve any unsteady flow problem. So here is the last problem in this chapter. That we are going to solve together once you write them down on your formula sheet, on a piece of paper, anything. Oh, by the way, this one looks ugly, so let me write this one on the right-hand side. Yeah, I can do that. Q in plus W in plus M in, H in, V in square over 2, gravity, elevation Z minus Q out plus W out plus M out. This one has enthalpy, kinetic energy, and potential energy. It's gonna be this one, U2 minus U1 plus moving boundary work, or H2 minus H1, or U2 minus U1. So this one is constant pressure, This one is constant volume. Okay, so that is the energy balance equation. So based on that, let's solve this problem together. So this is the energy balance equation. On insulated means adiabatic system. So we can neglect heat transfer Q. A vertical piston cylinder device initially contains 10 kilograms of water and 6 kilograms of which is in the vapor phase. Oh, that means we have a saturated mixture at the beginning. So where is the initial condition? This one, number 1. So at the initial state, number 1, we have 6 kilograms of which is in the vapor phase. That means 4 kilograms of which is in the liquid phase. So how do we determine quality X? Mass of vapor over mass of liquid plus mass of vapor. And we have 6 kilograms of vapor over out of 10 kilograms. So what is the quality X? 0.6. The mass of the piston is such that it maintains a constant pressure process. Okay, so it's a constant pressure process, H2 minus H1. At 200 kilopascal. So P1 is 200 kilopascal. That is the same as P2. Now steam at 0.4 megapascal and 360 degrees Celsius. That is at the inlet. So at the inlet, we have 0.4 megapascal. P at the inlet is 0.4 megapascal. Oops. My bad, this one is a typo, not 0.4, this is just 4 megapascal. 4 megapascal. And temperature T is 360. T in is 360 degrees Celsius. Is allowed to enter the cylinder from a supply line until all the liquid in the cylinder has vaporized. So what is the phase change process in the end? Saturated vapor. Now we have information about the final process. Number 2. Now it is pressure P2 is the same as P1, 200 kilopascal, and it is phase change process number 4, saturated vapor. Now that's all we know. We want to determine the final temperature and the mass of the steam that has entered. So let's solve this problem. So if this is the schematic of our piston cylinder device, we have one inlet and constant pressure process at 200 kilopascal. And there's no exit. So if you look at the general energy balance equation, now we know there's no exit, so we can remove m dot at the exit. There's no information about energy transfer by work, so you can neglect W in and W out. You can neglect kinetic energy change and potential energy change. So what do we have? M in, H in, the enthalpy at the inlet, the enthalpy at the final state, the enthalpy at the initial state. So that is the energy balance equation. The energy balance equation is M dot M at the inlet times H at the inlet is going to be H2 the total enthalpy at the final state, M2H2 minus H1, the initial enthalpy, minus M1, the initial mass times specific enthalpy. So this is the energy balance equation. What about mass balance equation? There is no M out. So mass balance equation is M in is M2 minus M1. M in is M2 minus M1. That is the mass balance. This is the energy balance. So, and we want to determine what? The mass flow rate, a mass of the system that has entered. That means we want to determine M in. M in. This is what we want to determine. Okay. So let's solve this problem. So we know the initial mass is 10 kilograms. So M1 is 10 kilograms. Do we know H in? Yes. We know pressure and temperature. If you know pressure and temperature, can you determine its specific enthalpy? Yes, we can. Oh, we need to determine the phase change process first. So we have 4 megapascal and 360 degrees Celsius. So we are going to make a property diagram using one of the properties. So I'm going to use this 360. So at 360 degrees Celsius, we can make pH diagram. This pH diagram looks like this. To complete this pH diagram, we need to know P sat, HF, Hg. So what is P sat? At 360 degrees Celsius, oh, I have a pressure table. No problem, I can make pH diagram. So at 4 megapascal, let's make pH diagram. pH diagram looks like this. And we need T sat, HF, Hg. So where can we find T sat, HF, Hg from this pressure? So let's go to pressure table. At 4 megapascal, where is it 4 megapascal? That's a 200 kilopascal, that's a 400 kilopascal. Oh, there's a 4 megapascal. At 4 megapascal, T sat is 250.4. So this T sat is 250.4 degrees Celsius. Then what is the temperature of our system? 360. So where is 360 on this TH diagram? Greater than 250. So what is the phase change process? Number 5, superheat vapor. So once you know it is superheat vapor, you can go to superheat vapor table, table A4. At 4 megapascal at 360 degrees Celsius, H, the specific enthalpy is 3,117.3, no, 2. So this H in is this value, 3,117.2. What about H1? We know pressure and we know the quality X. So it is saturated mixture. If we have a saturated mixture, how can we determine its specific enthalpy? By using linear interpolation. So H1 is HF plus quality X times Hg minus HF. Where can you find HF and Hg? From this pressure. So let's go to the pressure table. At 200 kilopascal, HF is this number, Hg is this number. So let me write these two values here. Hf is 504.7. Hg is 2706.7. Hf again 504.7. Quality X is 0.6. So can you determine H1? Yes, you can. H1 is 1825.4 of 0.84. What about H2? At number 2, we know it is saturated vapor at 200 kilopascal. So it's going to be Hg at the given condition, 200 kilopascal. So what is Hg at 200? What is Hg at 200? 2706.7. 2706.7. Now, we have everything. Can you determine M2? Yes, you can. M2 is 31.46. So from this, M2 is 31.42 kilograms. Define the temperature and the mass of the steam that has entered. Oh, mass of the steam that has entered. That is not M2, that is M in. So M2 is 31.46. What is M in? This one minus 10, so 21.46, right? So this is M2. So what is M in? M in is going to be 31 minus 10, 21.46 kilograms. And we have one more question. The final temperature in the cylinder. What is the phase change process at the end? Phase change process number 4, saturated vapor. And we know the pressure. So what is the temperature of saturated vapor? The saturation temperature at 200 kilopascal. At 200 kilopascal, what is the saturation temperature? 120.2. This is the temperature at the end. That's how you solve this problem. Any question? Any question? So here is the temperature at the end. 120.2. So that, yes. Oh, 31. You have two equations. You have M2 here, M1 here. These two are unknown. These two are unknown. So you have two unknowns and two equations. Mm-hmm. So that completes chapter 4. You have a new homework assignment. It's due a week from today, so it's going to be next Thursday. Please make sure that you completely understand all the problems in the PowerPoint and the homework assignments, because in the second exam, you will see similar problems, right? You all know that, the thermodynamics, there is no surprise. All the problems that you are going to see in the second exam are going to be similar to what you solved. Yes. After we finish chapter 5. So it depends on how fast we can finish. So if we finish chapter 5 this coming Tuesday, the exam is going to be the following Tuesday. If we finish chapter 5 Thursday, it's going to be next Thursday, but chapter 5 is much shorter than chapter 3 or 4. So I guess if we finish, in time, it's going to be, I need two classes, so it's going to be next Thursday, we can finish chapter 5, or the following Tuesday. So the exam is going to be at the earliest Thursday, 2 weeks from now, or the following Tuesday. Of course, it depends on how how fast we finish chapter 5. So if you want to have the exam too as soon as possible, you don't ask any question. If you want to have an exam later, then you can ask many questions to delay our progress, right? So that's everything for chapter 4. Any question? No? Now, chapter 5, the second law of thermodynamics. So we studied many open systems, such as nozzle, diffuser, turbine, compressor, etc., etc., etc. So what we are going to do is that we are going to combine them. We are going to combine, let's say, heat exchanger, mixing chamber, or the turbine or compressor, trying to make a system, trying to make a cycle. So we are going to study 3 cycles in this chapter 5 to understand how we come up with how we can combine multiple open systems to make a cycle. So we are going to study 3 very simple cycles, but widely used in our engineering, the industries. They are heat engine, refrigeration system, and heat pump. So these 3 are the cycles that we are going to study. What is a heat engine? It's a theoretical cycle that we produce, the mechanical, the work. So we use heat engine cycle when we produce what? Electricity. So the Rankine cycle that we just showed, the earlier in today is a very good example of, this heat engine cycle. Refrigeration cycle is, of course, the what we use in our refrigerator. So how we pump heat from a low temperature and dump it into high temperature. And what is a heat pump? Heat pump is very similar to a refrigeration system, but you're not very familiar with the heat pump, right? No? Yes? You know what is refrigeration system? Because we see refrigerator every day, right? I saw my refrigerator this morning. You saw yours this morning, right? But heat pump is also a type of refrigeration system, but we use a heat pump to heat a house, to heat a building. So we are actually using a refrigerator to heat a building. Okay? Make sense? So let's talk about, the one simple example. I'm pretty sure that you have a pretty good knowledge about heat engine. This is how we produce, the mechanical power using a turbine, so we can produce electricity. And you have a pretty good knowledge about, what is a refrigeration cycle. We, the transfer heat from low temperature to high temperature. Now the question is, what is heat pump? Do you have a heat pump? I have a heat pump in my house. So we can run, we can heat my house in winter. Instead of, the burning fossil fuel, you can run your refrigerator to heat your house. Sounds interesting. So let's see how it happens. So heat pump So we are going to talk about, the one by one, but, just trying to give you a brief introduction about, the something that you are not very familiar, okay? So give me about 5 minutes to tell you, how it works. So this is a house. I'm not majoring a painting, so, but it looks like a house, right? There's a window. One is not enough. Okay, so 2 windows. Door, oh, right, door. To the left or to the right? But there's not much space. So let me put door on the left. So there's a door to the left, okay? Yeah, I can put them. A skylight, solar panel. Yeah, but I'm not a big fan of solar panel. My research is solar energy industry, but I don't like solar panel. Look ugly. It looks ugly. Huh? Okay. Which color? Red. Okay, so flower, right? Okay. No more. No more. Okay. So let's assume that we have a conventional heater. Of course, you can think about, okay, gas-powered heater or electricity-powered heaters, but for simplicity, I'm going to talk about a heater using electricity. So this is a conventional heater that you can buy from Walmart. So if you go Walmart these days, they have a small portable, the heaters. And when you buy a small portable heater, the what number do you see first? Price, of course. You're a businessman, right? Why you're become an engineer? Because we like, the business, right? If you don't like business, you can go to physics department or chemistry. We chose engineering because we like science, but also we like money. So let's put them together. That's an engineer. No? That's right. Because if you go physics department, we study very similar things in mechanical engineering. If you or electric, the electric engineering, or if you go to chemistry, you can also study similar things in chemical engineering. But we want to put them together. We want to think cost effectiveness rather than just pure science, right? Anyway, so when you go buy a heater, you first look at the price tag and what is the next one? Huh? Yeah. So in this classroom, we use SI unit. So what is SI unit for that? Let's talk about, the watt. Okay? Power. When you buy an iron, you look at, when you buy a microwave, you look at the, the price tag first, and then what is the next one? Wattage, right? How fast it can heat, right? So the general one is going to be 1,000 watt microwave. If you pay more, you buy maybe 1,200. If you pay more, 1,400, and it goes up, right? So usually to heat a room about this size, maybe you need 2,000 watt, 2,000 watt heater. Let's buy 2,000 watt heater. What does it mean? It means every second that heater is going to consume 2,000 joule of electricity. Then when you consume 2,000 joule of electricity, how much heat do you get? 1,000? 15,000? No, not 15,000. 1,500? Pick a number. When you spend 2,000 watt, 2,000 joule of electricity, how much heat do you get? Oh, so you pay 2,000, you get 1,200? No. So Wait. Okay. So if you spend the 2,000 joule of electricity, you get 2,000 joule of the heat. There is no surprise. You get what you pay, right? So when you consume 2,000 the joule of electricity, you get 2,000 joule of heat. Is that right? It is right, because you are spending a useful energy, that is electricity. You are converting this useful energy into heat. How useful it is? No useful. It is the waste form of energy. So how difficult it is to create a waste? Super easy. If I want to turn this one into a garbage, I can do that. There's a trash can, throw it away. So if you have a 2,000 joule of expensive electricity, is it hard to convert this 2,000 joule of expensive electricity to a garbage, not trashy heat? Super easy. You just need a electric register. Just pass it. It will generate, the heat from 2,000. It will convert 2,000 joule of electricity to 2,000 joule of heat. So what is the conversion rate? What is the conversion efficiency? You spend 2,000, you got 2,000. What is the conversion efficiency? 100%. So when you go Walmart and buy a heater, something's showing that, oh, that's a very efficient heater. Yes, it is very efficient heater. That is always 100%. If you go over there and there's another heater, oh, it doesn't say, it is efficient. Oh, so that's not efficient. No, that is also 100% efficient, because you are, the converting useful energy to waste energy. So when you buy a heater, 2,000 watt of, the heater, what you are going to get is going to be 2,000 watt of heat transfer to the house. Okay. So that's the traditional heater. So let's talk about heat pump. I just told you that heat pump is a type of refrigerator. So let's see how we can install a heat pump. So I'm going to buy a refrigerator. Four minutes. So that's a refrigerator. You don't like it? Okay. A French door. Better? Really? No. 3-door is better. No, the best one is 4 doors. There's a middle one here. So let's look at the price tag. 200, 1,000, 2,000, and 4,000. Right? But let's not talk about that, okay? So once you buy a refrigerator, I'm going to remove all the doors. So there's no door. So it's just, so there's no door inside. There's no door in the front. I don't know how to draw a refrigerator without door. There's milk inside. There's a meat, red meat. So now I'm going to put this refrigerator. Oh, there's a door. Let's remove the door. So I'm going to remove the door. So that's completely open. I'm going to put this refrigerator this way. So there is a refrigerator. And this is the front of the refrigerator. So anybody can come here and then grab this food. There's no food, by the way. So you install a refrigerator on the door and then remove the door and then power in. Let's assume that this refrigerator is going to consume 2,000 watts. So what does it do? Yes. Okay, so that's a refrigerator. You remove the door and then place this refrigerator on the door to your house. So facing outward. Okay? So now, when you turn on this, when you power this refrigerator, what does it do? Generate heat. Yes, by how? Let's talk about heat. Let's talk about heat. Why do you buy a refrigerator in your house? Yeah, right. You want to, to remove heat from the food, right? So you want to remove heat from this inside to the outside. So by spending 2,000 watts, you are transferring heat from inside to the outside, let's say 1,000 watts. That's why, when you have a refrigerator, it's hot in your kitchen, and that's what, it warms up the kitchen air, right? Now, you spend 2,000 watts. And what is the final form of energy? What is the final form of energy? Heat. So this 2,000 watts becomes what? Heat. And then you are removing heat from the food, but there is no food, so air outside. And that heat is going to be pumped into the house. So you spend 2,000 watts. And how much heat do you get? 1,000 plus 2,000, 3,000 watts of heat goes into the house. Make sense? That's how heat pump works. Does it make sense? So you are spending 2,000 watts to run this refrigerator, and this gonna be first electricity, mechanical energy, and etc., 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 and finally heat. And you are pumping, the heat from this low pressure outside, cooling air, cold air, and then to dump this heat back to the house. So you're spending 2,000 watts, but what you get is 3,000 watts of heat. That's how heat pump works compared to traditional heater. Just trying to give you an idea about what is heat pump. So what we are going to do next week is going to be, we are going to study how to analyze heat engine, refrigerator, and now what we know, and now we know what this heat pump is. So we are going to analyze those 3 cycles. Okay, that's all. Thank you.